In order to understand the dimensions of vector spaces as well as how they are generated, we need to review through a brief concept known as linear independence. And this concept comes up quite often in the area of statistics, at least more advanced statistics. It's a very, very important concept. So this is the idea. Suppose that we have two vectors, A and B. And I denote these vectors by, of course, A1, AN. They're the same dimensions. I should say same size, just to avoid any possible confusion. I say that A and B are linearly independent if I cannot write A as a scalar multiple of B. All right, so put differently, if given one vector, the question is, can I write the one vector in terms of the other vector? Is that possible? Geometrically, what that says is if I have one vector and I have another vector, okay, they're linearly independent if that other vector is not on that same line, right? If it is on that same line, we say that they're linearly dependent. In this case, if they're dependent, you'll notice that when we subtract or add, because k can be a negative number, it doesn't matter, but whatever, I'll use subtraction just so that you're clear from the equation. You know what, let me use a minus sign here, just to be consistent with other things here. Okay, if this is true, the two vectors are linearly dependent because I can move this to the other side and write A in terms of B. If this is strictly less than 0 or strictly bigger than 0, they're linearly independent. And well, okay, I shouldn't say less than because these are vectors, not quantities. But let me just say, all right, first of all, when I say 0, I mean the 0 vector. All right, so 0, 0, 0, okay? Second, they're independent if they won't add up to 0, into the 0 vector. Now, that's just for two vectors, but as it turns out, I can extend this definition generally. So I say that the collection of vectors, I'm going to switch to the X notation here. I say that the collection of vectors are linearly independent if I cannot find, or rather, if the only multiples, the only way I can get them to add up to 0 okay, is if all of the alphas are themselves equal to 0. In other words, if I can find alphas which are not equal to 0, and this holds true, that means I can write one of the vectors in terms of the other ones. If the only way this is true is if they're all 0, I can't write one of the other vectors in terms of the others, because I can't divide by 0, right? In other words, suppose I manage to find a bunch of alphas that are all not 0, or maybe some of them are 0, whatever, okay? That means I can rewrite x1 as minus alpha 2 minus alpha n, right? And then divide both sides by alpha 1, and I'm able to write the vector in terms of what we refer to as a linear combination of the other vectors. All right. In this case, they are linearly dependent. So just to wrap up, A linear combination of vectors is one where I multiply each vector by a number taken from the real numbers, and I add up all of those vectors together. If the only way to get these all equal to 0 is if all the alphas are 0, okay, that is, if alpha 1 all the way up to alpha n are all equal to 0, then we say that these vectors are linearly independent. The reason is I can't write one vector in terms of another vector. It would be impossible. On the other hand, if there exists at least some I in 1 to n, or I should say an I and a j, 1 to n, such that I can write the I, or such that alpha I is bigger than 0 or less than 0. Meaning it's not 0, it's some number. That means I can write the vector in terms of a linear combination of the other vectors. Xi minus 1, whatever. Xn, not including the I, okay? The I is not in here, all right? If that's true, then I say that they are linearly dependent. For example, the vectors, if I take the vectors 2, 3, and 1, 3/2, okay? The question is, are these dependent or independent? Well, notice that I can write 2, 3 as 2 times 1, 3 over 2. Why? Because multiply that times 2, and I get 2, and then I get 3, right? Because I found a non-zero constant to convert this vector into that vector, these therefore are linearly dependent. What about 1, 0, 0, 1 and 2, 3? Are these independent or dependent? Well, these are dependent. I can write the vector 2, 3 as a combination by doing 2 times 1, 0 plus 3 times 0, 1. So because I was able to take two of the vectors, multiply them by any real numbers or specific ones to get that vector, these therefore are linearly dependent. However, you'll notice that if I have the vectors, let's say, let's say 1, 3 and 3, 2. Okay. Question is, can I find a constant such that the vector 1, 3 is equal to 3, 2? Well, let's think about it. This is the same as 3 times k and 2 times k, which means that 3 times k would need to equal 1, and at the same time, 2 times k would need to equal 3. Now, if you solve for this, you'll notice that divide both sides by 3, and k is equal to 1/3. But if I plug 1/3 into here, I get 2/3, which obviously it's not equal to 3. So it's impossible for that to happen. Therefore, because it's impossible no matter what I choose for k, there's no way I can get, for all values of k, this to be written in terms of this. And therefore, these are linearly independent. So when we talked about the span of vectors, any vectors, okay, we're going to get this is the collection of all linear combinations of those vectors. Okay, that's what the span is. I take the vectors and I generate a vector space. These don't need to be linearly independent, however. However, there is a theorem, I'm not going to go through it, but it basically says for every vector space, including those that are spanned by vectors, I can find a collection of linearly independent vectors such that the span of this is equal to the span of these. In which case, the number of linearly independent vectors is referred to as the dimension of the space. So for example, we know that the vectors 0, 1, and 1, 0, if we were to span those, all right, 0, 1, and 1, 0 are linearly independent. I can't write one as the other. You can try, okay? You can try, and you can say, all right, well, let it be some constant times this, which we know is just k and 0. But you'll notice there's nothing that I can choose for k to get the bottom number here to be 1. Therefore, they're independent. But remember that theorem we talked about. That theorem we talked about was that the dimension, if the dimension of a subset is the same as the dimension of the set, the two sets are equal. Remember what we talked about in the previous example. We said that we have 1, 3, and 3, 2, and we showed those were linearly independent. Well, because the dimensions of each space are the same, we must therefore have, interestingly enough, 1, 3, and 3, 2. That is, I can generate the same collection of vectors using linear combinations of these, which is equal to any number times this plus any number times this. But as it turns out, I can do the same exact thing with different constants, representing them as linear combinations of these vectors. Okay, so here's the net of it. If I have a vector space and I have a dimension of that space, let's say n or m, not to confuse things, then if I take any m linearly independent vectors from that vector space, then I can span the whole space using those two vectors. Okay, that's the net of all of this. Anyway, that's those are the fundamentals of linearly independence. How can we tell? I've showed you how to implicitly determine whether or not two vectors are linearly independent. How do you do it for 3 or 4 or 5? Well, that's going to entail a little bit more of a complicated method, which we'll talk about in the upcoming videos.